A warm welcome to part 2 of the webinar series around async await. Today we talk about the task parallel library and message pumps. So again, I'm Daniel. I'm a solution architect working at Particular Software. I live in central Switzerland. If you want to know more about me, I suggest you listen to episode 77 of Developers on Fire podcast by Dave. You can reach me on Twitter under @DanielMarbach. I blog on the Particular blog and on my personal blog, planetgeek.ch. I hope to see many subscribers on the Particular blog and of course on my personal blog. So let's do a brief recap from the last webinar. So in the last webinar, we learned that we should be using task.run, task.factory start new for CPU bound work. We should be using tasks directly for IO bound work, and we should try to avoid async void and instead return a task. Furthermore, we learned that if you're writing libraries or frameworks, we should prefer to use configure await false, and if we can, we should be async all the way, so we should not be mixing blocking code with asynchronous code. In this webinar, we are going to explore how we can combine async await with the task parallel libraries, the potential pitfalls we will discover when we combine async await with the task parallel library, how we can throttle our concurrent operations, and how we achieve graceful shutdown. The webinar itself is again divided into 3 parts. In the first part, I describe a little bit what a message pump is and what its applications are. Then we go into the code, and then we do a quick wrap-up, including a Q&A session, again, like last time. In this webinar, we will be diving in much more code, so it will be much more code-centric, and the complexity of this webinar is potentially much higher than the previous webinar. Please don't worry, at the end of this webinar, you get a link to the code samples that I'm showing, and you will be able to walk through the code step by step on your own. Of course, I'll also be available to answer your questions after this webinar series is over. So let's dive into the message pump. I have a little diagram here where I visualize the message pump. As we can see, the message pump is an infrastructure piece which is concurrently consuming messages from a message queue. When there are messages in the queue, the message is picked up, inspected, and based on the information on the message, a corresponding piece of code is invoked in your system. A message pump could be consuming messages from a queuing technology like RabbitMQ, MSMQ, or Azure Service Bus, and of course many more. In NServiceBus, the code which is invoked follows a certain convention, like it implements an interface called iHandleMessages. But since we are looking at the generic message pump, we will just assume that the pump will call any arbitrary method. Message pumps are not only useful for queuing technologies, they are also applicable to much more. For example, in an actor-based system, a pump could be responsible to dispatch calls to existing actor instances. Other examples of message pumps can be found, for example, in Windows Form. The URL thread in the Windows Form application is basically pumping window messages to controls which handle those messages. It's important to note that a message pump is a pull-based model and not a push-based model. So in the world with reactive queues, we would not be using a message pump, but that's a topic for another webinar. So now we already know what a message pump is, but how do we build a message pump in code? Let me dive into code directly and not waste any more time with slides. So a message pump, as we can see here, is basically just a while loop that is calling a method. The pump itself should be scheduled on a dedicated task, since we don't want to block the calling thread with the pump operation. That's why we wrap here this while loop, so the pump itself with a task.run. The method that we are calling inside the loop is called handleMessage. It is an asynchronous operation and it doesn't block the calling thread. We simulate the work here with task delay so that the work approximately lasts for 1 second, 1000 milliseconds. The pump loop itself needs to abort it somehow when we want to shut down our system. Here, shut down means we're just walking out of the unit test and make it successful. One way to do this would be to just use any arbitrary bool flag. But in the async TPL world, we have a construct called cancellation token source. The source provides a cancellation token, as we can see here, which is linked to this cancellation token source. As soon as the source is cancelled by using either cancel or cancel after just makes the source cancel after a specific time period is elapsed, then the state of the token transitions into cancelled. We can observe or query the state of a token by polling this property here, which will return true or false depending on the state, or we can use a method which is called throw if cancellation is requested. Of course, if we use the method throw if is cancellation requested, like shown here, we would be throwing an exception, which might not be what we want to achieve. It really depends on the design of your code. We could also pass the token here directly to the task.run method. I will not do this right now. I will cover this later in the code samples. Awaiting the pump means that we will be waiting until the inner loop here is totally completed, and then we dispose the token source, and then the test is over. So since we are letting the loop, the message pump, run for 1 second, and one operation here simulated by task delay will last for 1 second, we should be seeing, as we see here in the output, just one pumping operation when we execute this code. Let's do this. We execute the code. As we can see, we have one pumping operation and the test is successful. So now we have a basic understanding what the message pump is. A while loop, which can be cancelled. And the while loop will call any arbitrary method. So a message pump itself can be running for multiple minutes, hours, or even days before we shut down the system. So the pump itself is a long-running operation. The task parallel library offers a way to hint the TPL about the operations that are running inside the task body. These hints can be passed into more advanced API under task.factory.startNew. Let's see such an example. So we could be using task.factory.startNew, and we could be passing in a flag called long running to indicate that this operation might potentially take a long time. The problem or the impact of this long running flag is that the current task schedule will create a new background thread. We can observe this by looking into the reference sources of the thread pool task scheduler. Let's see that. So as we can see here, if we enqueue a task and the long-running flag is set, what happens internally is that we create a new thread, the thread is background flag is set to true, and that thread will be working on the given task. So let's go back and let's think again what we learned in the last webinar. In the last webinar, we talked about that every await statement is an opportunity for the worker thread to step out and do other things. So when the body reaches here the first await statement, then the thread associated on the scheduler will be completed, and all the stack and memory, etc., which is allocated for the thread will also be garbage collected. So that means we will be wasting unnecessary resources if we are specifying the long-running flag as we did here. By the way, the same applies for attached to parent here. If we're using attached to parent, that's also not really properly working if we have true asynchronous operation inside a task body. Another caveat of using the task.factory start new, as we've seen here, is that as soon as we mark the body of this task as async, what this method returns is a task of task. A task of task is a proxy of a task. What is a proxy of a task? A proxy means that this task here does not represent the inner loop, the inner operation of the task body. It represents the proxy of that inner operation. So when we await the pump task directly, it would be completed although this method inside here is not yet completed or cancelled. In order to properly await a proxy task, we will need to first unwrap that task, and then we get the original task, and then we can properly await it. So as we can see based on this example, we should always prefer, unless we are really knowing what we're doing, task.run over task.factory.startNew. In the intro, when I explained the message pump, I also talked about that the message pump potentially handles messages concurrently. As we've learned in the previous webinar, we can handle operations concurrently by not awaiting the handle message. Let's see how this looks like. So as we can see here, we have the same loop, and we, instead of awaiting, so sequentializing the loop, we are just returning the task and associate it to a local variable. By that we can spin off concurrently operations inside the message pump. The problem is that when we are shutting down, we potentially want, or at least that's my design decision, we want to wait until all concurrently running operations are successfully completed or cancelled. We can only do this by tracking the task instances. How can we track the task instance? One trick to do that is we can use a concurrent dictionary of task. We can add the return task to that concurrent dictionary as a key and as a value. And then of course, this dictionary, if you would only do this, would grow indefinitely, and at some time our solution would essentially suffer out of memory issues. In order to not suffer from out of memory issues, what we can do is we should clean up the running tasks dictionary, so the tracking dictionary. We can do this by adding a continuation to this running task. That's also why we have this local variable here. So we can then do a continuation, and inside that continuation we can remove the task which is passed into the continuation delegate from the dictionary. Another thing I'm showing here is that we have here this task continuation option, execute synchronously. Execute synchronously is a kind request to the TPL to try to execute this continuation here on the precedent task, or on the thread which handled the precedent task, while it's transitioning into the completion state. So this is a slight optimization which should only be applied when you can be sure that the method in here will not take too long and is synchronous. I said it's a kind request. It's a kind request because it can happen depending on the current thread pool or on the task scheduler, that the worker thread which previously handled the running task is aborted. And in that case, if that happens, TPL will make no guarantees that this continuation is actually executed on the same thread. So it will be scheduled, and another worker thread will take care of executing this one. But it's an optimization we can apply. We just have to remind ourselves that it's not always going to work. But it's okay in this case because we only track the task instances, the running task instances, for shutdown purposes, which we then await at a later time. If we miss to remove a few tasks, that doesn't really matter because we are shutting down our system anyway. So like in the previous webinar, we're using here task.whenAll to await all the running tasks. So we await first the pump to be completed, and then we await all running operations. The problem of this code is that we are in an unbounded way just executing potentially hundreds or thousands of tasks. So we are essentially scheduling as fast and as many tasks that my machine allows us to do. The implications of this are, let's imagine inside the handle method here, you'd be using, or you'd be creating SQL connections because you want to access your database. So what happens? If we create in an unbounded way SQL connections, we will eventually, or I'd say pretty fast, deplete the connection pool, and we would get an exception which potentially tears down our whole app domain. There is also another low-level technical detail which is happening here. Since we are scheduling an unbounded number of tasks, that will lead to ramp-ups on the thread pool. A ramp-up means that the scheduler heuristics indicate that there are many tasks waiting in the current scheduler, and the worker threads are no longer capable of handling all those tasks. What happens then is that this task scheduler or the internal thread pool starts allocating new threads, new worker threads, and gradually ramping up. And ramping up is an expensive operation, and therefore, while we ramp up, we also decrease our throughput on the messaging. So how can we achieve concurrency limitation? If we Google for task and concurrency limits, you might stumble over a class which is called Limited Concurrency Level Task Scheduler. The problem of this special task scheduler is that although it is called Limited Concurrency Level Task Scheduler, it limits the number of threads associated to work on task. As we learned in the last webinar, when we have tasks representing true asynchronous IO-bound operations, a single thread can easily handle hundreds of those tasks concurrently. So what we need here is a semaphore. Allow me to switch back briefly to the slides. So we will be using, in the next example, a counting semaphore. A counting semaphore can be compared to a toll booth. Like in the picture on the right side, you have 8 lanes and 8 toll booths. So the count of the semaphore will be 8. Every time a car passes the semaphore, the count is decreased. When the counter reaches 0, then no cars can pass the toll booths. The cars will eventually queue up behind other cars until free slots become available again. We will be using the semaphore slim, which is the only semaphore in the .NET framework which can be awaited in an async manner until slots become available again. So let's switch back to the code. Let me expand the code a little bit. So let's go to the limiting example. So we create now a semaphore slim with 2 slots. The semaphore allows us to asynchronously await the free slots, like shown here. So inside the message pump, we now await free slots. So if the first one enters here and the count is still 2, we can pass here and do our operations. Then the next pump comes in and there's still slots available, and the third pump comes in and now the slots are depleted. So what happens here is that the third one will asynchronously wait here on this method until more slots become available again. We can release the slots by calling semaphore release. What we do here is we do it in the continuation. So just before we do our housekeeping, we release the semaphore, allow other operations, asynchronous operations to continue, and then we execute our previously shown housekeeping code. Since we have now operations which are awaiting inside the body, so as you can see here, we have an await statement, we need to mark the body async. Let me go back to compare it to the previous example. In the previous example, we didn't mark this method body here async because we had no async, we had no await statement in here. We didn't need to mark it async. But here, since we now await the semaphore slots, we have to mark this one async. Now, since the continuous method, as we can see here, returns a task, we need to tell the compiler that we intentionally do not want to await this task. So one way we can do this is, as we can see, we get a compiler warning. We could do a compiler warning CS4014. We could essentially just insert a pragma here and disable that warning because we intentionally do not want to await it. But a much more convenient thing to do, or a much more expressive thing to do, is to write an extension method which takes care of this. This is a neat trickery you can use. As we can see, this extension method does nothing inside the body, but the compiler thinks that we are consuming this task. So with that, we can even give this a better name like ignore or intentionally do not await the return task or something like that. So that if someone is reviewing this code, they know that it was a conscious decision. But this code, again, has a slight problem because we could essentially just capture the asynchronous options. Like if we have two slots here and the slots are already taken, as I explained previously, what happens is that multiple operations can be waiting here. Since we use wait async without any time limitations or without any cancellation token, this means when we want to shut down our message pump, the message pump task could potentially hang indefinitely. Well-designed async APIs usually provide overloads which allow to pass in the cancellation token. Those APIs will observe the cancellation token and throw an operation cancelled exception when the token is cancelled. So let's see how we can do this. So we have the same code, but now instead of just do wait async, we pass in the token to this wait async method. So if we are cancelling the cancellation token source, the token will be cancelled, and this line here will throw an operation cancelled exception, and all the pending operations which are waiting here will be cancelled, and of course the inner things will not be cancelled because we're not cancelling those. The downside of this is that since we're throwing an operation cancelled exception, the task representing the pump will transition into the cancelled state. So when we await a task which transitioned into the cancelled state, this task will throw an operation cancelled exception when it's awaited. If we want to do graceful shutdown, we need to ignore this cancellation exception. We can do this by writing an extension method like here and do a try await task configure await false catch operation cancelled exception. So with that, we can gracefully shut down our code. Of course, this is a conscious design decision I took. You might want to do it differently, but I'm showing it here how you can await operation cancelled exception by using this design. Of course, in the previous example, we just used the handle message method. The handle message method was just doing task delay without actually observing the cancellation token. What we can do is instead of using the handle message method, we could use this one, handle message with cancellation, where we can pass in the cancellation token. So now it's possible, even for the user code, to observe the cancellation token, and if it's possible, to cancel any operations inside the handling. Of course, that again is also highly subjective to your preferred design. But I want to show how you can cancel even operations inside your code. So that's it. We now build gradually a message pump. Now let's dive and let's see how the whole code would look like. I know this might be a bit overwhelming now, but since we gradually build up the code samples, I'm showing you again the full code. Here, concurrent dictionary, semaphore slim. This time we're using 100 slots. We're letting this code block run for approximately 5 seconds. We have a token source. The only thing that is different here is that we have here a counter, which is interlocked increment, just to count the number of tasks. We pass in the cancellation token to the handle method. We track all the tasks. We release the semaphore. We remove the completed task from the tracking dictionary. Again, we ignore the continuation. And then we await the pump itself, and we await all running operations. We dispose the token source, we dispose the semaphore, and then we just output what kind of throughput we get. So let's execute this test here on my machine. It will take 5 seconds, so we have to wait a few seconds until we'll see the console output. As you can see here on my screen, on my machine, we consumed 501 messages with a concurrency of 100 in 5 seconds, and we got a throughput of approximately 100 messages a second. So far so good. Let's go back. What would happen if we had the same pump, but we would have an operation which is not truly async? Let's zoom in on the operation which is not truly async. As we can see here in this code, I now have a thread sleep. A thread sleep means this method here is now blocking. So any worker thread entering this method will be blocked for at least 1 second. If we know that we in our architecture are calling code which is blocking, what we can do is we can wrap the method, here the blocking handle method, in a task.run. So we force the scheduling of a task of this method. So all the rest of the code is the same. We again track this task, but this one returned by task.run. We do all the cleanup again. So that's the only difference. As you can see here, again 100 concurrent slots, again 5 seconds. All the rest is the same. Now let's execute this piece of code. It takes a while until it's completed. As we can see, it already takes much longer than the previous example. Now it takes 11 seconds. The previous one took 5 seconds. And what we get now is we consumed 139 messages with a concurrency of 105 seconds. And that gives us roughly 27 messages a second. Let's switch back. 100 messages a second, 27 messages a second. As we can see, the true asynchronous version has almost 3 times more throughput. So our message loop with true asynchronous operation is much more efficient. So another thing I want to briefly show you is that if you want to build something like a Node.js system, or if you want, for example, an actor-based system where you want to limit the number of worker threads associated to do the work, even with true asynchronous consumers, what you have to do is you have to wrap it in a task.run or task.factory.new. In order to limit the number of threads associated here, now we can use the limited concurrency level task scheduler. Surprisingly, although it's bad name, as we can see here the integer we're passing in is now called max degree of parallelism. As we can see, the parameter passed into this method properly talks about parallelism, but the name here implies concurrency and not parallelism, which is kind of weird. But anyway, so let's set it to 1. So what happens is we will have at just 1 worker thread available on this scheduler. What we have to do, we have still the same code, still wait async with the semaphore, but now we're using a task.factory start new because we want to provide the scheduler. As we can see here, we provide the scheduler, And that means all the tasks scheduled on the schedule will only be executed by one worker thread. This time we're using a special handle message method to show this flag here, which is called hide scheduler. Hide scheduler, we have to specify that if we are doing this approach, because if we don't specify it, what happens is that every code in the body of this task will see our limiting scheduler. What does it mean, we'll see our limiting scheduler? Let's execute this code briefly. With hide scheduler, we see there is no output in the console. We consumed a few messages and that's it. Let's go back and remove this hide scheduler thing. And now let's see what I'm doing here. What I'm doing is I'm outputting, I'm querying the task scheduler.current and I cast it to a limited concurrency level task scheduler, and if that is not null, then I output limiting scheduler, and even here, just for demonstration purposes, have a task factory start new inside this handle method, which does the same thing, task scheduler concurrent as limited concurrency level task scheduler, and then I output here, even here, limiting scheduler. So let's execute the same code again and see what happens. As we can see, our operations, our handle methods now observe the limiting scheduler. So it's crucially important if we use custom scheduler and we invoke third-party code, we should always be specifying the hide scheduler creation options.
Unmuted.
From the code perspective, and let's go back to the slides.
Daniel?
Yes?
This is Mauro. May I interrupt you for a second? There's a question that is correlated to what you were just talking about. The question is from Blaze.
Yes.
And Blaze is asking, why would you put a limit on the number of slots in your pump? Which is the rule you rely on to decide it is needed, not needed? Which is the limit you should choose and things like that?
Okay. That's highly dependent on your domain. For example, I mean, we know that the connection limit when we do SQL connections is the default value is 100. So I mean, you can imagine if you set it yourself to 200, you will be depleting the connection pool if you know that your framework, your library, your application code will be creating SQL connections. So in that case, I think you should set it to a value potentially lower than 100 to not deplete the SQL connection pool. So the answer is it depends. I'm sorry.
Thanks.
Okay, so let me do a brief recap and then we can go back to answer more questions. Okay, so we just saw in the previous example that you should always prefer task.run over task.factory.start new unless you're doing really special things like I showed in the end. But in the majority of use cases, you don't need to do these fancy trickeries. I just showed it for the sake of this webinar. You should be using cancellation tokens to cancel operations inside the task.bodies. You should use a semaphore slim to throttle instead of a custom task scheduler. And you should not be using long-running or attached to parent when you're creating tasks, when you're executing asynchronous operations. And of course, as we've seen, you should be non-blocking all the way to maximize the throughput in your applications. So in the next webinar, we will be talking about NServiceBus, specifically about the to-be-released version V6. And we will talk about how the V6 API update helps to avoid common async await pitfalls and makes your code ready for asynchronous APIs in the cloud. I hope you join again. Briefly before we go to Q&A, the slides and links, they are here again on my GitHub account. Britt will also send out the link in the notes. And let's go to questions. Mauro?
If I recall correctly, you should have also a hidden sample that you may show us.
Hidden sample?
Well,
No, that was the hidden sample.
sorry. Sorry, I got it.
Oh, no problem. Any questions, Mauro, from the audience?
I'm waiting for them to come in. And in the meantime, let me ask you one question. Is there any counterindication in using, well, let me rephrase the question. Which is the difference between using thread sleep and task delay inside a task? So something that is run asynchronously inside the task.
Okay. Yeah, I think I mentioned it, but let's do a brief recap. So if this method, so if a worker thread is entering here and we have a thread sleep, we block the worker thread. So that means we capture the worker thread, and that worker thread coming out of the thread pool of the scheduler will not be able to do anything else. When we have this, sorry, I need to scroll up a little bit. When we have this version here with task delay, when a worker thread is entering this method, for the time for this 1 second, the worker thread will not be captured, and therefore it can go back and work on other tasks scheduled on the scheduler concurrently. That's the difference.
Okay, there's a question from John asking if the sample you've shown are basically reproducing the approach we are using internally in NServiceBus.
Yes, they are. Yeah. For example, we use this approach for MSMQ, and since so let me go back to the code. Since MSMQ is a bit, let's say, an older API in the .NET framework, because it's not really async enabled, what you would see in NServiceBus is not this version of the pump. You would see this version of the pump for MSMQ, because we know that the receive operation, which is I/O bound, but unfortunately the API provided by the .NET framework is not async enabled, so we have to wrap the receive operation from MSMQ in a task.run. So you would see potentially this version of the pump. Hope that answers the question.
Okay, thank you. So Blaze is asking, in the last sample, he was surprised that the non-hidden scheduler was not visible in the inner task. So when you remove...
okay, yeah, I think it is. It's just, I think it should be, he means this one, right?
Yes.
Yeah, it is. Let me run it again. It should be. I think it's just. Let's boost it up a little bit. I think it's a demo problem, but let's see if I can show it. It's not. Yeah, it is visible. He has to trust me now. Of course, potentially. I have hide scheduler here, of course. Yeah. See demos. Okay, let's run it again. Wall of did you see?
Yes.
Here? Can you see it?
Yes. Yes. Yep.
Cool. I'll stop it and let's scroll down to show it again. As you can see here. Yeah. Okay.
So there's a
more questions?
Yeah, there's a comment from Rihad that is saying that, well, that is related to the comparison between the task delay and the thread sleep, and is asking, basically saying, in practice, any useful job will be blocking. So which is the advantage of having a non-blocking task.
In practice.
Yes. So
I'm not sure if I understand this question.
I suspect that it relies on the fact that, correct me if I'm wrong, if the entire chain is async await enabled, so it is task enabled, what happens is that the job you are calling can optimize the usage of resources and maybe could be slightly faster instead of blocking entirely, because then the other step can be itself optimized and async await enabled, and so on and so on and so on. It's obvious that at a certain point work needs to be done, and that work will consume resources.
Yes, I mean, if we have an IO-bound domain, and that IO-bound domain, like I explained in the last example with MSMQ, doesn't provide any async-enabled API, we are pretty much left with wrapping in a task.run. There's nothing else we can do. The same applies if we have inside an IO-bound domain, we have things that needs to be executed CPU-bound and potentially in parallel to improve the performance. We need to use construct like task.run inside that call stack. But of course, the better thing would be in your design, in your architecture, to completely separate IO-bound from CPU-bound code paths, if you can, of course.
So there's a question from Christina that is asking, what do you do if the order of processing the messages is important?
So what do you do if the order of processing? Okay. I mean, she means in my example, or
I'd say both in your sample and as a general question.
Okay, so good question. I think what's important to note, and I didn't say that the semaphore slim in the .NET framework doesn't preserve the ordering. So let's say first iteration, second iteration, third iteration, and whatever, we would be running two things would be concurrently waiting here. So what it means is, it doesn't mean that the first one will be released. It can also be that the second one will be released, or vice versa. So the ordering is not guaranteed. But since we have a queuing system, and the queuing system is a first in, first out, if we would only have this code involved without things like error handling, retries, and all that stuff, when we would do it single-threaded, we would preserve the ordering. But of course, in reality, that's never the case, because in reality, we will be doing it concurrently. We will have things like retries. So in case of exceptions, what we will do, for example, we will take the message out of the queue. We will process other messages, and then we will put it back into the queue and start consuming again. So therefore, the ordering of messages is not guaranteed. So the best thing is to accept that fact that even with queues, the ordering is not guaranteed.
So basically, we can say that message ordering and concurrency don't play well together. So it's
yes, and I mean, if you really need a system which preserves in a guaranteed way the order, it's probably useful to use something else than queues, like an append-only locker, which you can read sequentially.
So another question is, are there any drawbacks of using task.wait instead of await?
Here, so I assume this one, task.wait, wait all, wait any? Is that the question? Or is it here? That's difficult to know. Here.
I suspect that this is this one. Yes, this one.
Okay. Okay, so I explained it that also in the last webinar. The difference is it's a blocking operation, and the other one is not. I mean, since maybe in this example, and since we're executing this in a unit test or on a console application, we could even say, you know what? Since these are the top, in my example, since these are the top level things we want to wait for when we are shutting down, for example, in the console application, we could definitely say, let's do just the wait or dot result, because it doesn't matter. It would matter, like shown in the last webinar, if you do this inside a call stack. But if it's on top level, you can always choose between both approaches. But just don't do it inside the call stack. Because again, wait result means blocking, like thread sleep. Okay. Thank you very much again for listening. I hope you enjoyed the webinar and see you next Thursday.